Hello, everybody in EE418. With Professor Derrickson out today, I will be giving this guest lecture on the topic of Acousto-Optics. My name is Liam Hayes, as you can see. I am a master's student currently at Cal Poly in the electrical engineering department. I may know some of you, may not. Um, but irrespective of that, I hope that you guys are doing well, having a good quarter, and yeah, it's time to get going on this lecture. So a little bit about me before we really get started. I did my bachelor's in electrical engineering at Cal Poly. I was here from 2017 to 2022. I took a quarter off and then I returned here for my master's degree, which should be done this spring. I had an internship at Keysight Technologies in High Frequency Technology Center, HFTC, early last year. Some of you may have, be familiar with Keysight or have also had internships with Keysight. Um, some of my specialties, just to kind of give a bit about my credentials so far. My specialty is in the field of semiconductor device physics as well as micro-nanofabrication of these devices. So my knowledge set spans from digital device domain to high frequency devices, a bit of MEMS stuff, micro electromechanical systems, as well as of course optoelectronic devices. Most of my work thus far has been in the context of creating and designing biosensors. That has been the topic of my both senior project and my master's thesis. I've also done some research on emerging material devices, such as 2D material devices and neuromorphic structures. In terms of the micro nanofabrication side of things, I'm very familiar with both traditional CMOS processing slash BiCMOS processing, as well as 3.5 process technologies. Most of which that knowledge set I've accumulated either here at Cal Poly as well as at Keysight Technologies during my internship. Okay, so let's get going on this lecture. I hope everyone's excited. A little bit of a history regarding the topic of acousto-optics. So some original experimentation was being done by Mandelstam starting in 1918. He claims to have sort of figured out some of the different principles involved in the acousto-optic realm during this time, but did not publish any of his findings until roughly 1926. Before 1926, of course, though, Léon Brion, my apologies on pronunciation for any French speakers in the class, had formed numerous theories, and many of the models that we commonly use today in the field of acousto-optics, not just in acousto-optics, of course. Brion, very famous physicist, did a lot of work in solid state regime. But he determined most of the effects that we now know today to be true by about 1922. He was a theoretician, however, so most of his theories were unconfirmed until um, Gross, Mandelstam, and others kind of did some more experimentation over the years, excuse me. So then by 1932, however, basically everything that we know today had been figured out, disregarding maybe a few of the more niche theories or a few of the more kind of esoteric functionalities that we apply acousto-optics to. So here's just pick images of here's Brion himself, and then here are the father-son duo, the Braggs. So this is William Bragg, this is Lawrence Bragg, father-son duo in, let's see, in 1915, they were given a Nobel Prize for their joint work and, namely the law named after them, Bragg's law, where they were studying different crystallographic structures, utilizing optics to do such. So moving on, we're going to start this presentation or this lecture going over some of the fundamentals. From the fundamental portion, the first thing to note is Bragg diffraction. So up here, you can see that we have just very conventional Bragg's law. I hope you guys have seen this before. My guess is you have somewhere, whether it be potentially in EE402 or if you've taken solid state physics or earlier in this course. If not, here's the law. It simply states that your refractive index and the wavelength of the incident light based on diffraction within crystallographic planes of a periodic structure. Note, by the way, this doesn't necessarily have to be a solid state structure. This can be a liquid structure as long as it forms some sort of a crystalline or periodic lattice type of structure. Yeah, within the internal dynamics of it. Bragg's law should apply. So again, yeah, William and Lawrence Bragg discovered this relation. They were working on Crystalline material analysis, largely, they were trying to determine different parameters such as lattice spacing as well as lattice types of many different materials. Um, most of which, at least in their terms of their early experimentation, were actually just on basic salt, NaCl, the salt that everyone uses every day, because it has a very nice, very interesting crystal structure, and it was also just very widely available to them. They were also working on some other um, more niche materials, such as zinc selenide, at the time when they discovered this law. And it is basically the gist of it is just saying that you can determine the spacing between crystallographic planes. Of course, this is kind of assuming a 2D model, so a very simplistic view of it, but you can extrapolate up to 3 dimensions. And then the incident light and the diffracted light are coupled. And so what you can do, they're coupled and then, naturally, and they're reflected off of these crystallographic planes. And then what you can do from there is once you perform the experiment, typically used in the context of an X-ray diffractometer, because Bragg's law traditionally is applied in the X-ray regime. However, it is very important in acousto-optics and as well as many other fields of optics, as we will see. Um, but the gist of it is effectively that as light diffracts off of these crystallographic planes, you can sweep the angle of your sample, given, let's say, an X-ray diffractometer. You're doing a diffraction experiment, sweep the angle of the material relative to the incident light. You can then observe different peaks and troughs in your diffraction pattern. And from there, you can determine many things about your crystalline sample. It's a little bit more complicated than that. You can use powdered samples, you could use monocrystalline samples, and each one will kind of give you slightly different results. Um, However, that's kind of the gist of it, and then you can pretty much back extrapolate most of the properties regarding the atomic structure, at least, of whatever material sample you have, given that it has some sort of crystallinity associated with it, and is not entirely down to the single atom amorphous type deal. Um, as that doesn't really exist, it's pretty useful. Most X-ray diffractometers, we actually have one on campus, up in the solid state physics lab in Baker Science. It's a fairly low power one, but it uses a very common X-ray diffraction source. It's a copper K alpha laser. Um, so if you guys would like to know more about that, then I believe there are a few professors in the department that typically teach that lab. Now I'm forgetting the number, but it is a physics, the course number, but it is a physics course. It is a solid state physics lab that you could take. Very interesting class. I do recommend it if people are interested in this stuff. So moving on from here. Now that we have kind of an understanding of Bragg's law, let's go over Bragg gratings or diffraction gratings, right? So typical gratings consist of either varying materials or varying geometries. This can be done, at least in terms of varying geometries, this can be done in a few different methodologies. So as you can kind of see from this image here, we have, there's this grating indicated here. Typically, the point of which is to have alternating refractive indices. These alternating refractive indices act as kind of many small reflectors that the incident light interacts with. And the net effect of the incident light interacting with these small reflectors is, at least in terms of macroscopic scale, is that you get some sort of reflection off of the net reflection, or as I call it, kind of a macroscopic reflection. Many use cases for Bragg gratings, you could use them in terms of coupling different optical media. So you can, if you're going from like one waveguide to a different type of waveguide, you can use Bragg gratings to do such. They can also be used in fiber lines as just kind of quasi-passive filters in a fiber system. As we shall see here, this is sort of the crux of acousto-optics, as well as many different electro-optic phenomenon. However, yeah, today is focused on acousto-optics. So here we just kind of have a general law associated. It's derived from Bragg's law, but it is general law associated with diffraction gratings. And so in this case, naturally, well, in this case, I've kind of jumped the gun a little bit and kind of given you guys a little bit of a hint or insight into what's coming up, where the capital lambda is, the acoustic beam wavelength. However, can also be kind of extrapolated upwards, just to say that it is the wavelength of the periodicity of your diffraction grating. Lowercase lambda, of course, is your incident optical beam. Taking into account the net or average refractive index of your medium, or you can also, in the acousto-optic sense, describe it as the unperturbed medium, where this theta sub b here, that term is simply your Bragg diffraction angle. And so it'll, that will determine the angle at which, based on, the relation on the right-hand side, the angle at which you are diffracting most of your light or reflecting most of your light. So some more fundamentals before we really get moving on, strict acousto-optic stuff is hopefully everyone is somewhat familiar at least with the concept of a phonon. If not, that's totally okay. You guys are not really expected, in my mind, to understand this quite yet. But just to kind of give a very simplistic view of what a phonon is, it is a quasi-particle. I know that might sound a little bit weird, but it is just a simple fact that we use. We model different phenomenon in solid state physics as quasi-particles, just because it makes the math a little bit easier, speaking honestly, or at least it makes it possible, let's say. So by a quasi-particle, we mean that it's not a technical particle, right? You can't observe the particle per se, but we model it mathematically as a particle, specifically as quasi-bosonic. So what we mean when we say quasi-bosonic particle is that it is a particle capable of doing work, which makes sense, considering the net or the typical kind of name that the typical thing we apply these phonons to, these phonon relations to, are lattice vibrations. And so as you can see here in this little diagram down here, here you can see we call this a 1D chain of lattices, or a 1D chain lattice. Specifically, use your imagination. This is a bit of a rough image, but think of these as diatomic atoms, right? So you could think of hydrogen 2, right? So yeah, just simple H2. And then what you can do from here is you can model each of the two interactions as a simple harmonic oscillator. If you really want to get into it, you can model as a quantum harmonic oscillator as well, but then you have a many-body problem on your hands, and that's a bit less trivial to solve for. So from a more classical perspective, you can inject we call it a block wave. Block wave is basically the same as a plane wave, where it is the same sort of wave that has, a plane wave front, if nothing else. And you can inject it, and then all of these atoms will kind of shake back and forth with each other. And depending on the energy at which your incident block wave is, hitting these atoms, as well as the frequency, of course, you can obtain different energies, right? Different energies are associated with the system. You can get different normal modes. For the most part, the waves are traveling. However, there are certain cases where you can obtain standing waves. It is much more difficult to do so. Now, mind you, these frequencies are very, very high. These are all, for the most part, plus 10 terahertz and then up. Very, very fast. But again, this is atomic motion. It should be fast. So, yeah, then from the phonons, that we have here, let's say, these are supposed to be tiny little springs, by the way, just to kind of give you guys an idea, with all these atoms bouncing back and forth off of one another. You can obtain these normal modes, and which are given by a relation we call phonon dispersion, which is kind of depicted up here. This is a phonon dispersion of this exact modeled system, where it is a 1D lattice of diatoms, excuse me, where you have what we call acoustic modes as well as optical modes. So the only distinction that we really give between acoustic and optical modes is the frequency at which they act on, right? And let me take a step back real quick. Many of you may have seen a relation like this, or other things called a dispersion relation, where we have, you have wave vector or your k-space on the x-axis, and then a frequency or an energy on the y-axis. Excuse me. So, if you've seen this before, great. If not, no worries. We can also model electronic behavior in the same way, and this is what gives rise to your band diagram. So I'm assuming everyone has taken at least EE418. If you remember the band diagrams you've covered, this is kind of a fundamental starting point, right? Except you would do it for electronic structures. These dispersion relations can be solved in many different ways. Of course, if you have something as simple as a 1D chain of lattice, you can do it pretty much analytically, which is kind of interesting. If you, of course, kind of extrapolate up, have a larger lattice, 2D, 3D, different types of crystalline structures beyond simple cubic structure, then you have to use more advanced theories as well as some numerical techniques to really pin down even an approximate relation on your dispersion here. But the main point is we will be focusing on the acoustic modes, right? The acoustic portion of the phonon dispersion here for the rest of this lecture. And it's not a part so much of the classical view of acousto-optics that's Brion strictly came up with. He did have something to do with kind of a more quantum mechanical view, as he utilized quantum mechanics fairly regularly in his work. But it's just something important to keep in mind as we move forward in the lecture, that this is something that exists. The acoustic modes, optical modes are important to have at least a slight understanding of. So as you guys will kind of see moving forward here. One last note here is, while we're, it might not quite make sense where we're, for an optics class, we're focusing on acoustic waves instead of the optical waves that kind of occur within a medium. It's the same thing. The only difference again is the frequency. Yes, there is a bit of an energy gap here, or a frequency gap here. No need to spend too much time thinking about it unless you're curious. But for the context of this lecture specifically, we will strictly be focusing on the acoustic portion. And mind you, again, the x-axis is k-space or your wave vector, so it is momentum dependent, this relation, which I think is fairly interesting. Moving on, another kind of way to view, excuse me, things, or another bit of fundamental background that I think you guys should have before we really get cooking on this, is phonon-photon scattering. So there are many different types of quantum mechanical scattering events, right? There's photon-photon, there's electron-photon, like Compton, namely called Compton scattering. There's phonon-phonon scattering. Basically think of a quantum mechanical particle. It can scatter off of something. Without getting too deep into the kind of explicit nature of scattering mechanisms, as they are very, very complicated in practice, if you're actually working with these day to day. The brief kind of overview of phonon-photon scattering is you'll have some phonon, just meaning you'll have some, again, modeled as a quasi-particle. So you'll have this quasi-particle at some frequency, therefore at some energy. Some incident photon will hit that phonon, it'll interact with it, and then it'll diffract. There are two ways that this can occur. There's a Stokes process and an anti-Stokes process, which you guys may be somewhat familiar with this terminology from different portions of this course. And if you guys haven't gotten there, then I'm guessing that you will get there as well. It has, one of the chapters in the texts covers it. I believe that the chapter regarding light matter interactions discusses Stokes and anti-Stokes processes fairly in depth, which is nice. But in this context, for the photon-phonon scattering or phonon-photon scattering, Stokes process just means that this scattering process will actually generate an additional phonon. So then you'll have a new photon carrying out. So take this image and just kind of another squiggle coming out here. But this takes energy away from the photon that is incident, and therefore the refracted or reflected photon at the output of the scattering event will actually have a decreased frequency relative to the incidence. Excuse me. In addition to this, we also have an anti-Stokes process, which I'm guessing you guys can probably guess is sort of the reverse of that, where you have a phonon being entirely annihilated from this scattering event. So that's kind of more so what's depicted here, where you have incident photon, phonon goes away, photon comes out, right? And what occurs there is that the photon's frequency is upshifted slightly, imparting a little bit more energy into it. Both processes are probabilistic in nature. They will both happen in an acousto-optic medium under acousto-optic conditions, basically when the things are turned on. However, ideally, you typically want some more of like an anti-Stokes process, although it really doesn't matter, as we'll kind of see here. This gives rise to what we call a Brion shift, and we will see in a bit that the Brion shift, while yes, it is technically there, it exists, needs to be taken account of in practice, specifically for this lecture, and then also just in general, it does not impart a large enough frequency shift such that it really needs to be taken into account under most circumstances. Only very specific circumstances will it need to be taken into account. This is a power limited process because, as I mentioned, it's a probabilistic process, as are all quantum mechanical interactions. And so the higher power you have, then the higher the probability of your Stokes shifting occurring. Up until a certain point, of course, you reach a saturation where you now have every incident photon is performing some sort of either Stokes or anti-Stokes process in your medium. Right. So, but then at low powers, you have much lower probabilities of Stokes and anti-Stokes processes occurring, um, which is just, kind of logical to a great extent. All right, so now let's kind of get more into the actual portion about acousto-optics and the kind of the mechanism, right? So the way I'm structuring this lecture is that there's going to be two views on acousto-optics that I'm going to try and impart to you guys. There's a classical view, which most of which Brown did come up with, and then the rest of everyone, Gross, Mandelstam, sorry, performed their experimentations and really got really pinned down the exact theories explicitly. And then there's also going to be a quantum mechanical view. That description will be much more brief, as it is a bit more simplistic in terms of the qualitative nature of it. So beginning with the Bragg grating, as discussed prior, that is sort of the bread and butter of the acousto-optic mechanism. The difference here is that there's no just physically ever present Bragg grating involved, right? So you can think of acousto-optic materials as it's a material where once you inject this acoustic wave, um, what you can get either traveling or standing waves, but let's assume a standing wave for the time being. Excuse me. Then what can occur is that within the standing wave in the medium, you will have, it's a pressure wave in effect. So this pressure wave will cause kind of regions of very local regions of higher density and lower density in terms of your lattice, right? So you'll have more atoms in one location, fewer atoms in another location, and then that will obey some level of periodicity, as we will kind of see. So these regions of, these locally altered regions, they have variant permittivities, just due to the density shift. If you have a different permittivity, you now have a slightly different refractive index. So it is a very, as you can probably imagine, it's a very sensitive effect. It is, yeah, it's not very strong in any particular medium for higher strength applications where when I say strength, I'm meaning if you need a really aggressive, a really aggressive sort of tunable Bragg grating, then sometimes you may tend towards using electro-optics, which can be found in the chapter following the acousto-optics chapter in the Tekin Soleil text. However, acousto-optics, kind of due to the size and their manipulability as well as the ease of fabrication, as I will touch on a bit more later, they're still favored in many different applications. Anyways, so yeah, you have these regions of kind of locally different permittivities yielding locally different refractive indices, and so you go from regions of higher refractive index to lower refractive index in a periodic manner. This, by definition, gives you a Bragg grating. The only difference now is instead of it being a stagnant Bragg grating, it is a tunable Bragg grating. What I mean by tunable is that you still have this lambda term here, which, as touched on, previously down here as well, that is the acoustic beam or the acoustic wavelength in the medium. So you can vary this, right, in a number of ways. So either you will be utilizing a piezoelectric crystal, which can vibrate on its own once you apply some potential to it. These piezoelectric crystals have multiple vibrational modes associated with them, so you can alter the potential applied to the piezo crystal to alter the mode that it's oscillating in. Or you can take a more kind of traditional, more simplified approach where you have your bulk material and you attach it to a pressure transducer, effectively just a small speaker. And from there, you can, if it's a speaker, just like you do when you listen to music or anything else, you can vary the frequency, therefore the wavelength of the pressure wave very easily, right? And so this kind of gives you that tunability, as you can kind of see here, where you can change the Bragg diffraction angle, which is effectively the angle. You can think of it as the angle at which the reflected light on the output of the acousto-optic device is at relative to the input, right, relative to the injected beam. So by purely varying that parameter, you can get some variation in your Bragg angle, which is kind of a neat little principle there, and will, as you'll see later, kind of allows us to make these devices more usable and not just kind of only good for one or two things. There is one, excuse me, there is one, or technically there's two criteria, one of which is noted here, um, for this to occur in the first place, however, and that is you need wave vector matching, right? And so here you have, the wave vector of the reflected beam is equivalent to the wave vector of the incident beam plus minus the wave vector associated with the acoustic beam or wave. I'm going to use wave and beam somewhat interchangeably throughout this because, and at least until we get kind of further on into the lecture. But typically when I'm referring to, just keep in mind, typically when I'm referring to any of the optical beams, if I say wave, I actually mean beam. And then when I refer to the acoustic beams, at least initially, I will be referring to acoustic waves. Down the line, I will make a more concerted effort to note when I'm talking about specifically an acoustic wave or an acoustic beam. That will be somewhat important in a bit. Anyways, you do have this, you could think of this as like a phase matching condition in effect, or a momentum matching condition, whatever, however your brain would prefer to think of it. But that is a criteria of this scenario. So, luckily, this sort of gets sort of encompassed in the Bragg relation, the standard Bragg relation, wherein if you are at a Bragg angle, a proper Bragg angle, given the rest of your system is set up properly, you will have this phase matching condition. There's also a frequency matching condition, which is kind of what I was talking about a bit earlier, in the sense of, when you have your Stokes or anti-Stokes process, and you have the reflected photon is shifted or downshifted, upshifted or downshifted in terms of frequency. Just as there is this relation, you can replace the K and Q with omegas if you so choose to, right? Omegas, or even, 2 pi f, right? Whatever you want to call it, however you want to denote your frequency. And this is, kind of interesting that it does occur. It is mainly due to the Brown scattering that occurs, which is just another fancy name for the photon-photon interaction that we have there. And it actually is, technically speaking, it imparts a Doppler shift on the reflected light in the medium, as it traverses through the medium. The reason why it's not as important, and I don't have it noted here, is because the acoustic frequency that you're going to be using is going to be pretty much in every use case, at minimum 5 orders of magnitude smaller than any incident optical beam that you're going to be injecting into your system. And that alone, as we will see in most types of practical use cases for these acousto-optic devices, whatever operating bandwidth that you're within, it's not going to matter, right? So unless you're dealing with some very funky system where you have very, very, you're performing some sort of very fancy modulation that requires huge separation for whatever reason between your operating modes, then you might technically be able to possibly have this be an issue, but for the most part, it won't be an issue. You're not going to be, yeah, the frequency shift imparted by the acoustic wave in the medium as it is applied to your reflected optical beam. It's not going to do anything. You're pretty much never going to notice it. That being said, it is still a technical condition, part of the Bragg condition that does technically need to be taken into account. And so, yeah, just keep in mind, I guess, if you're working with equations associated with this later, or if you just have a curiosity, beyond the scope of this lecture, keep in mind that that is a thing that exists there. So moving on a little bit, actually going back one step, one last thing to note here is that on both, I mentioned kind of up and down conversion. This applies to the phase matching condition as well that we have here, where hence the plus minus, where you can actually get positive and negative shifts in terms of your reflected beam relative to your incident beam, both in terms of the phase of it and the frequency of it. So what this kind of means in the net is that your angle of the diffracted or the reflected light, excuse me, at the output of your acousto-optic medium can either be shifted up or shifted down relative to kind of a z-axial normal, let's call it, or even relative to the incidence, depending on the collinearity of your system. So I think this is fairly interesting. It allows us to do some interesting things here. And if I remember right, that has something to do with whether you're doing a Stokes or an anti-Stokes process. So typically, if you have a Stokes process where, let's actually go back here real quick. Yeah, if you have a Stokes process and you generate an additional phonon, frequency of the reflected beam decreases, and so you're going to have kind of a downshifted angle, where in an anti-Stokes process you'll have an upshifted angle. So moving on, I kind of touch on that again here. You can see that. So this is what I'm talking about in terms of you have a downshifted angle and then you have an upshifted angle, both relative to kind of a z-axial normal. Z-axis is going this way, or you can even have it in terms of the transmitted light, right? Because with the incident light, there will be some transmitted, some diffracted. So yes, the up and downshifting conversions are possible as long as phase conditions are met, which, to a first order approximation, we can assume that they will always be met in the context, for the purposes of this lecture. As I, somewhat touched on earlier, again, this phenomenon can take place in both solid and liquid media. Here, naturally, we're going to be focusing on solid state media, as it's more useful and more common to see the acousto-optic effect in solid state materials. Again, typically piezoelectrics are used, but yes, also with some niche cases, you can just attach pressure transducers to a bulk medium if that medium is not naturally piezoelectric. Electromotive, if does not have that in its nature, then yes, a simple pressure transducer applied to the material will do the job just fine. Excuse me. So yeah, this is going to be here. We have a more in-depth view of kind of what's going on, at least from the mathematical perspective. So here, as you can see, technically speaking, this acousto-optic effect, where you have a variant refractive index, it is variant in both time and space. It is a periodic variation, as as your acoustic wave is a periodic, as we said, standing wave, at least in the context of kind of this first order approximation here. However, the neat thing is that aside from some very, very, again, very niche applications of this acousto-optic effect, you will not really be varying the phase of your acoustic beam. And so what you can have be considered here is that this whole spatial term basically stagnates. Or at least the whole time term here stagnates. And then so you can rewrite the spatial variation, or you can rewrite the variation in the refractive index as a purely spatial variation, as is denoted here. Just to go over some of these different variables, this is the net time and space refractive index variation. This is just going to be your average refractive index of the unperturbed medium. So this means that you have no acoustic wave is imparted to it. It is just a hunk of material sitting on a desk. This is the refractive index of it right here. And then you're going to subtract this whole term. So here, this delta n naught is going to be the difference in that average, or it's at least the magnitude in that difference of your average refractive index. I will go into that term specifically in a bit more detail in the following slides, as it is important and kind of gives you a main figure of merit when dealing with acousto-optics and designing systems. And again, it is a periodic structure, so it follows a cosine relation. The capital omega here is your angular frequency of the acoustic wave. Of course, you have your time, and then you have your wave vector of the acoustic wave interacting with your spatial term here. And then jumping over here, as I mentioned, you stagnate the time dependency on the acoustic wave, have it be a standing wave, and then the relation simplifies to have just a static phase term. So there's kind of an interesting relationship here. And in many cases, this phase term can be canceled to zero, which is mathematically convenient. And this is a fairly decent approximation. It yeah, you can use this approximation pretty broadly. So this gives a good general overview of sort of what's going on. In this figure sort of demonstrates that a little bit, where you have your peaks and valleys, your peaks and troughs on your standing wave in an acousto-optic medium, and this changes your refractive index. You have a region of high density, you'll have a higher refractive index. You have a region of low density, you'll have lower refractive index, and yeah, so this creates your grading, which is kind of nice. So as promised, a bit more in depth on that delta n naught term, or that magnitude term. So it is very dependent on the material parameter or the specific material that you're dealing with, namely through the elasto-optic coefficient, which is this term here. That is a very material specific constant. It's something you can look up in a lookup table, so I won't talk about it too much here. But you could think of it as kind of like a coercivity term almost, where it's how apt is the material upon electrical stimulation. In our case, an optical stimulation, which is same thing, different frequencies, right? It is how apt is the material to behave elastically. So how apt is it to have motion inside the material from the atomic perspective. So that's kind of an interesting little note here. This S0 term is the amplitude of the strain in your perturbed media. When I say perturbed media, I just mean that you have your material sample and you're perturbing it with an acoustic beam here. Excuse me. So this is kind of one nice little picture here, and of course being your average unperturbed refractive index. So this is a fairly simple relation here. However, to get to these some of these other terms like PS naught, then you might have to do a little extra work. So we can go down here and have another view of what this delta n naught term is equivalent to. It's equivalent to the square of 1/2 times this material parameter times the intensity of the acoustic wave. Of course, the intensity of the acoustic wave is very strongly coupled to the amplitude of the strain. I will not go over that exact relation. However, it is in your textbook. And just for future reference, before I forget to mention it, this is chapter 20 in the Tekin Soleil text. And so hopefully you guys all have access to that text at this point. This M term is typically considered a material figure of merit, as mentioned here. That might not mean too much, but it is sort of like a dummy term that we use to group all of these terms here. But this is a very important term. It gives rise and kind of gives a better depiction of how good is a given piece of material for acousto-optic applications. So again, we have the elasto-optic coefficient, which again, material parameter. Again, you have your average unperturbed refractive index, but then down here is when you kind of take more of the material parameters into account. You have this delta term, which can be the density of your medium. Of course, different densities will vary the strength at which you can alter your refractive index. You have a higher density material, then the pressure wave is going to be less apt to induce a very strong variation in terms of atoms bunching together and separating out. You have a low density medium, the reverse will happen. The atoms will be moving kind of all over the place. And then coupled to the density is you have your velocity of sound within that given medium. This varies depending on your medium, not quite as drastically as the speed of light typically, but something to be taken into account most definitely. Yeah, so then kind of a couple more points with this. So over here I have listed some common materials that are used in acousto-optics. So germanium surprisingly can be utilized, tellurium dioxide, silicon oxide, lead molybdenum oxide, as well as arsenic sulfide, I guess you can say. Those are common materials used. There's some other materials as well. As you may have probably noticed, germanium is not optically transparent. This effect can still occur in non-optical regimes, right? So this can occur in the infrared regime as well as the ultraviolet regime, and kind of going beyond. So naturally, as one would expect with different materials, you can widely vary the frequency of operation with these types of systems. You can dope these materials and the other associated acousto-optic materials to either increase your elasto-optic coefficient, or you can decrease it if you so choose to, I suppose. And you can also vary the density, assuming you have substitutional doping. Which, yeah, substitutional doping in effect is just what occurs when you have some sort of thermal doping process, meaning you have some diffusion occurring. So let's say you have a material sample, you apply your dopants to the surface of that sample, you throw your sample with your theoretical dopants into a furnace, and the high temperature from the furnace increases the diffusion rate of your dopant into the material. Initially, at least, those dopant atoms will they'll diffuse what we call interstitially, meaning between lattice sites or between atoms within the lattice that's already there. However, given a long enough period of time or enough heat, then what can happen is that these dopant atoms will be apt to kick off one of the atoms already kind of contained within your lattice, and then we call it a substitutional dopant, or an activated dopant is another piece of terminology used very commonly. Excuse me. I know that was a bit of a side note, but no, I think that's kind of an important part to note there. Yeah, it gives you guys a bit of an idea of how that process works. So to kind of, get a little bit more into the math here is what we're going to do these next few slides. So naturally, a very big important portion of this is you want to know how the amplitude of your reflected wave is, you want to know what the output is of your system while you already know the input. And so to do this, we have a mathematical relation, which I believe Brion did derive this mathematical relation in the first place for your amplitude reflectance. And so the general term of it is given here, right, with the lowercase r being in your amplitude reflectance. This equation is coupled with this image, so you can view this image as this is your acousto-optic Bragg grating. Let's just call it that. You have your incident light and your reflected light. And you have a length L that this effective Bragg grating is traversing across, and you have L sine theta. I'm hoping this is kind of ringing some bells with Bragg's law here. Anyways, this integration is a fairly interesting one, yet fairly simple. You have a phase term taking care of this exponential right here. The integral spans across across the entirety of your effective Bragg grating here. Excuse me. With this drdx term simply being the infinitesimal complex reflectance amplitude, and specifically its infinitesimal how it varies in space. And then down here, you can see this is kind of a more descriptive form of that, where, yeah, you have, again, the infinitesimal complex reflectance amplitude relative to your space. It's equivalent to the infinitesimal change in reflectance relative to the infinitesimal change in refractive index you could almost say per individual grating. You can multiply that by how your index of refraction changes in space, and you get kind of this nice relation over here, which is descriptive of how your reflectance varies given infinitesimal change in your refractive index, again, with kind of a tacked on phase component to go along with things. So the general view being taken here is that, with these infinitesimal terms involved, you can say, okay, what if I only have one diffraction grating, let's call it, where you have one variation in your refractive index, one switch of it. Then you can model that as one system, and you can say, okay, we know that a very small percentage of the light will be reflected off of this grating, just because you have a change in your refractive index. This is we all know that this occurs. So what happens if you have a lot of these bunched together? Well, that's where the integration comes from. So that is effectively how simple this integral is in terms of the qualitative perspective. I think it's a pretty neat way of thinking about it. It does make sense. I think it's nice that it makes sense. A lot of the math that we see in upper level electrical engineering courses sometimes doesn't make sense, but this is kind of a nice little relation we have here. So then the integral, of course, like I mentioned, extrapolates throughout the material medium, assuming that you have many different refractive index alternations involved, which in practice you will, because these acoustic waves will typically be pretty fast waves relative to what we commonly think of acoustic waves. I'm talking in, tens to hundreds of megahertz sometimes, but very much, well seated in the tens of megahertz. So you still have, quite a few localized regions of condensed matter and slightly more separated matter. So we can take that initial integral and we can note that, the general relation for how you expand a complex sinusoid, right, in terms of its exponential terms. So you can break it down as such. And, yeah, here, here's your sine term up here and this side, this exponential, you can do all the rest. As well as, you can come down here and apply it to this cosine relation here. Of course, sine and cosine, just a phase shift away. So you can apply this relation, expand your sinusoid in terms of its natural exponential terms, and you can rewrite your amplitude reflectance integral as this big old long boy right here. No need to get too lost in the math here. I will pause if you guys want to write this down because I think it's a fairly interesting mathematical relation that we have going on. So I'll pause a few seconds before continuing. Okay, great. So I hope you guys kind of have all this written down where, yeah, you have this really long integral. Note that you'll have kind of this positive term here and this negative term here. This is somewhat important moving down the line, as you will have both positive and negative influences on your reflectance. Remember how I spoke about earlier how you can have your Stokes and your anti-Stokes shifting. That's what these positive and negative terms come from. So you can either have a relative positive angular increase on the reflected beam relative to your z-axis, or you can have a negative negative angular shift. So that's where this plus and minus comes from. At least from the qualitative perspective. From the mathematical perspective, it comes from here and the fact that you can split your complex sinusoid into two complex exponential terms. So it's kind of neat how you could actually see the math, for lack of better terminology. So doing this, we have this R naught term that pops up here. That is simply this. So that stems from this relation down here a little bit. You can manipulate some terms there and obtain this R naught term. Substituting for this phi or Vod phi, technically, we have the acoustic wave angular frequency multiplied by the time term, and that's what's injected here. So it's a fairly simplistic change of variables that we have involved. And once you carry out the integration, I'm not going to go over the exact carrying out of this integration, as that would take quite a bit of time, let's say. But you eventually end up with this final relationship that we have down here. So I've mentioned you have kind of a positive and negative, excuse me, relation here, corresponding to your angle of diffraction, be it positive or negative relative to your z-axis or your incident beam. It does obey a sinc function law. However, it is a fairly shifty, a very spicy sinc function, let's call it. There's also a phase shifting component that is taken into account here. So yeah, I'm hoping this is kind of helping you guys put some pieces together in terms of the mathematical relation. So, as mentioned, as I, again, further point out over here, you have your up and down conversion. This applies to a 2D model where you have an incident on you have your beam path, the path of both of your beams, incident and reflected on your z-axis, and then let's say you have an x-axis that can sweep up and down in terms of your angle, or some angular axis, however you want to view it. You can view it in Cartesian or cylindrical coordinates or your spherical coordinates, depending on the types of wavefronts you have. Here, we're going to be entirely focusing actually on plane waves. So that's actually, so that's another thing to keep in mind. All the analysis thus far, as well as for the rest of this lecture, takes into account incident plane waves from your optical waves as well as your acoustic waves. And then we're going to assume that any optical beam is a Gaussian beam. And so, yeah, so this gives rise to the angular sweep that you can perform in this 2D case. Then if you extrapolate up to 3D, then you can sweep, on your X and your Y axis, let's say, where, you kind of have a 2D image that you can create as opposed to a 1D image that you can create with your reflected beam. So, you have your amplitude reflection, but in addition to this gives rise to an intensity reflection, right? So this intensity reflection is simply modeled here. So what happens with this kind of ideal relation up here, this is going to be down here, by the way. So this is a more general relation that you have associated with your intensity reflectance, whereas up here is an idealized variant where the theta involved in all your, in all the equations that you're using to model, which are, for pure intensity reflectance, it's very similar to your amplitude reflectance. It does obey a power law, and as noted right here. So if you take the angle of your reflection here is at your Bragg angle, then you can note, fairly simply that your intensity reflectance is your absolute value of the R naught term squared. So R naught, you can think of it as kind of like a baseline amplitude reflectance, or a DC component, if you will, of your amplitude reflectance, because there is some tolerance on this. Yeah, there's some tolerance on this, both in terms of your angle as well as in terms of the amplitude. And then again, you have your more general term down here, which takes more closely into account sort of some of the material parameters that you have involved, as well as the acoustic wave more explicitly. So this is all both intensity and amplitude reflectance, as I note here. It depends on the polarization modes involved, but for at least this intensity reflectance equation, this assumes a TM mode of polarization. Let's say the first TM mode, just for simplicity there. So kind of pushing forth. There's, so far we've pretty much just been talking about what happens if you have acoustic waves in your medium, so your bulk medium. So let me get back to another image of this here, where pretty much the entirety of the medium is oscillating from your applied acoustic wave. It is important to note, actually, before I delve too much deeper into the next point here, that although with this image, this image kind of shows that just in the middle portion here is where your acoustic wave is traversing. In practice, especially if you have something like a piezo crystal, effectively the entirety of the medium will be oscillating in accordance with the acoustic wave. However, the grating involved and the diffraction of the light that's occurring pretty much almost exclusively happens in a very kind of small central region of your medium. This is born from your phonon modes that I discussed earlier, where most of the action is kind of occurring wherever your central point in the lattice is. So that's where typically most of the energy is going to be taken into account. You could think of this, if you want to think back to sort of your quantum mechanical modes, right? You have your electron trapped in a square well. You have, your distinct modes, M=1, M=2, M=3, and so on and so forth, giving rise to different energies. For this, you can kind of treat it as if every mode is the M=1 mode, where you just have a single one, you take basically just a half wave, right? And that half wave relation is indicative of basically all of your action occurring right in the middle here, in terms of, the potentials involved and the energies involved. So that's just something to keep in mind, that, yeah, when dealing with these types of materials, these types of systems, the acousto-optic effect in general, the diffraction occurring from your acoustic Bragg grating, let's say, happens pretty much in the middle of the sample. That being said, however, if you have an explicit beam of your acoustic beam, as opposed to an acoustic wave traveling, throughout the entirety of the bulk, you have some, some more finitely confined acoustic wave going through here, or acoustic beam in this case now. Then one of the many different phenomena that can occur is called Raman-Nath scattering, or Raman-Nath diffraction. So as the name suggests, Raman and Nath both kind of figured this out. I don't believe they were working together explicitly. I believe they figured this independently, just roughly at the same time. So we give the name, we attribute this effect to both of them. So what occurs in this effect here, let's focus on this top image here, is that if you were to inject a traveling wave as opposed to a standing wave into your medium, then you can kind of get with this, this thin acoustic beam, then you can get roughly the same effect as we've had before. However, now it is irrespective of any Bragg angle. So this is kind of an interesting effect. There are not too many materials that can accommodate the Raman-Nath effect relative to general Acousto-Optic materials. But it's still kind of an interesting effect that occurs. It is born from this, this relationship upon the angle, so you can still do things like perform scanning of the diffracted or reflected light here. And this image in particular shows an even more interesting effect, in my opinion, where if you have two standing waves creating a traveling wave here, then under the Raman-Nath conditions, then you can get a reflection pattern like this, where you have the transmitted beam, optical beam coming from your incidence, your incident light, and then you also get you have both a plus minus theta relation here. Whereas prior, if you remember when we were talking about more conventional acoustic waves through an acousto-optic medium, you can get either or, pretty explicitly just either or, even with a standing wave pattern involved. Here, standing wave pattern is indicative of now you get both. So you can get kind of much nicer, beam splitting characteristics, allows you to do some fancy things. This, however, as kind of noted by this diagram here, it is still dependent upon your phase relation and your frequency relation. So those conditions do still need to be met, where you need to have, your two reflected waves. They can only be phase shifted or momentum shifted, however you want to think of it, by the acoustic beam and relative to your incident optical beam. So this condition still needs to be met here, as well as the frequency matching condition that needs to be met. But as you've probably noticed, and as I mentioned, that's much less important here. While technically still involved, it's something that's not quite as commonly taken into account. Just because it's of relatively little importance in terms of any application here. Excuse me. Moving on slightly, higher orders of this effect can also be achieved. So you can actually inject higher order modes of your an acoustic beam. So basically just meaning, you have higher harmonics, you can inject higher harmonics of your two traveling waves to create even fancier patterns in terms of the acoustic wavefront here. This allows you to enact this Raman-Nath effect. However, now you can do it with multiple modes. So again, incident light, transmitted light, but now you can have up, n modes effectively, depending on how many modes you have of your acoustic beam, of plus n minus theta reflection here. So this allows you to greatly separate out your light. However, again, if we assume Gaussian beam, the neat part is that at the output of each will also be a Gaussian beam, its own Gaussian beam. This effect will be kind of useful in a little bit here. This is interesting stuff, though. Okay, as promised, here's sort of a more quantum mechanical view. Again, we have this description of the phonon-photon scattering. And again, as opposed to an index or a fraction change, what you can at least internally view this effect as is that you have your acoustic wave going through a material medium that creates localized regions of higher density and lower density in terms of the atomic structures. Mind you, just very slightly, right? I'm talking these atoms are moving at most a couple of angstroms, right? So very, very small levels of movement here, but it is still enough to observe these effects naturally. So what happens is, let's say put yourself into a region where you have an acoustic peak, right? So you have a localized region of high density, right? That's where you're sitting. You have all these photons coming in, and now since you're in this high density region, you have a lot of atoms. A lot of these atoms are vibrating with one another, right? Due to the effects they're feeling, just from the crystal, the thermal effects that they're feeling, as well as the exchange interactions that they're undergoing, and all the rest. There's the natural motion, as well as, of course, there's 0-point energy as well. But ignoring, getting too deep into that, you're standing there, and there's a lot of atoms. When there's a lot of atoms in a location, there's a lot of lattice vibrations. When there's a lot of lattice vibrations, you have a lot of phonons. A lot of phonons, when light is, hitting you, in that region means that your probability of a phonon-photon scattering event increases drastically. So this is kind of nice. And then of course the converse is true when you move yourself to a region of lower density, at least locally lower density. Instead of viewing it as a change in refractive index, you can view it as, well, there's now a lower probability of a phonon-photon scattering event. And so doing this in a periodic manner will give you kind of the same net results, as has been discussed earlier. So here are these two equations. There's not too much mathematically going on here, at least in terms of the context of this lecture, getting too deep into the mathematics of this particular quantum mechanical view for the mechanism is a bit beyond the scope of this lecture, definitely beyond the scope of the lecture, and probably a bit beyond the scope of the course in general. If you are interested, unfortunately, the TCAN/SLA text does not have too much more of an in-depth description of the quantum mechanical view for Acousto-Optics. But there's definitely some good resources online that you guys can look up if you are curious at all. I recommend it. I think, this is a very interesting topic naturally. But generally speaking, you need to have the same phase and frequency relation here. Excuse the slight error here. This second H bar should not be here. It should be tacked onto the reflected wave vector here. But yes, you have, it's all now, instead of just having explicit angular frequency and phase matching condition, you tack on an H bar, right? A reduced Planck's constant, quantize the system. And once the system is quantized, the modeling of it, at least in terms of the qualitative or phenomenological, maintains very similar stuff to what I just described to you guys. So now we kind of get to move on to some of the applications of Acousto-Optics. There are many applications. I will not be talking about every single one. Excuse me. Because there are definitely quite a few, and to reach some of them, let's say, you have to use the coupled wave theory, which I have not gone over just due to the sake of time, as well as just the complexity that would bring. That would be a bit beyond the scope of this course. If you would like to know a bit more about a coupled wave theory as it applies to Acousto-Optics, it is described briefly in the TCAN/SLA text. In my opinion, the description of it in the text is not necessarily the best. The textbook does not quite do the best of jobs explicitly describing the coupled wave theory relative to how well it describes kind of the other theories that I have discussed here. But feel free, absolutely read it, read through that if you so choose to, or try and find other resources for it, because it is, it does allow you to approach some other more fancy use cases of Acousto-Optic materials. But in any case, one of the larger use cases, or one of the larger types, like classifications of devices for Acousto-Optic materials are modulators. So you can have Acousto-Optic modulators, or AOMs, as are typically called. And what they will do is they can be used to, kind of turn on and off your diffracted beam. So again, let's say you have your incident light, right? They have this sort of cone pattern here, but it can be whatever pattern you so choose. And let's say you have no acoustic wave involved here, so there's nothing going on. The light is just going to transmit right through the material. And it'll come out on whatever's over here. It'll be injected into whatever else is going on in your system on this other side here. And then if you so choose to, you can then turn your acoustic wave on, and boom, diffraction will occur pretty immediately. It is important to note that in most cases, in most cases, you're not going to get 100% diffraction of your light. You can get, in some cases, you can get up to 99.9% diffraction on your light. And so those types of materials, those types of systems are useful in Q-switching lasers, where you can, sandwich in between your one end of your gain medium and one end of your mirrors, or one of your mirrors in your resonator cavity there that you have your gain medium placed in order to create your laser. You can have an Acousto-Optic cell that behaves exactly in this way, where you have very, very high reflection percentage there. And then just kind of give a qualitative perspective of how you can use it in a Q switching laser, excuse me, is that you can have, you can have the resonator do its thing where the beam is resonating, and each pass of the optical beam being resonated traverses through a pumped gain medium. This, of course, amplifies your signal, as it should. Um, and you can do it in such a way where, let's say you have your acousto-optic cell turn in the off state, so it's not diffracting, then your laser light will be emitted. But let's say you want to kind of build up a little bit more, you want to build up some of your amplification in the laser system. You can have diffraction be occurring for finite period of time, so you can have a very low Q, low quality system at that point, and switch it into a high Q system by turning off your acousto-optic cell. So you guys will need to kind of keep that in mind moving forward, because Professor Derrickson has asked me to provide you guys a set of homework problems, which I will present to you at the end of this lecture. And quick hint, this slide's a bit important. So yeah, you guys can have fun with that as you continue. But in any case, a bit more on this modulation effect. So there's a finite bandwidth associated with modulation, which you can kind of get an idea of what's going on with that here, where you'll have your diffracted beam, it'll kind of take the shape of your incident beam in this regard. However, there will be some spread to it in terms of the angle, right? Because you're traversing light through a medium, you will have some spread of your beam no matter what. And so this still occurs, but it occurs in the form of a very specified bandwidth. So this modulation bandwidth occurs here. And so, naturally you can use this as sort of a frequency shifter in addition to just a more standard modulation technique. Because, in an ideal case, we have just one center frequency that everything's involved with. In practice, does not occur. You get your Brion scattering, you have your different types of shifting mechanisms. And this will, it will impart frequency shifts kind of toward the edges of your reflected or diffracted beam. And so this finite bandwidth can be modeled here, where it is, it is very material specific, which is kind of nice. This delta, by the way, is no longer the density. This is the delta theta terms. This is a coupled delta theta term. This delta theta term is, as you can see here, is the spread. In most problem sets, this delta theta will be given to you, as it is in many of the problems kind of contained within the book, if you so choose to kind of take a look at those. Yeah, so this is one major application of acousto-optic materials is just modulators. Another application is scanning. So what you can do, as I touched on before, right, is just by varying the frequency of, or the frequency, therefore the wavelength of your acoustic beam or your acoustic wave, in either case, that is traversing through your medium, that alone can change your Bragg angle, which changes the angle of diffraction that your incident light is being reflected, right? And so you can use this to perform a scanning type maneuver, in a simplistic view at least, because there's more complicated techniques, which I'll touch on in a second. But you can have just a conventional scanning mechanism where, assume that this is not a beam, assume this is a standard standard acoustic waves, pressure wave going throughout the material. You'll have your incident light. By varying this frequency alone, you can have the diffracted light scan up and down, just as is kind of shown here. Here's an equation relating your scan angle with this B term being your bandwidth that we determined earlier, in terms of modulator. Excuse me. With the scan angle, however, there is a finite number of resolvable spots given by this larger function down here that you can see. So this D term that you see here, that is the width of the incident beam. Just to keep in mind, right? So yeah, that is, yeah. So you have the relation there, dependent on your acoustic velocity in the medium, as well as the finite bandwidth of the medium that which can handle. Excuse me. There's a few different types of manipulations that can be done to an acousto-optic material in order to perform the scanning maneuver. And so one of which is here, you can have they're here they kind of phase shift mechanism where you can have one standard beam or acoustic signal being injected, perform phase shift to it, and get a constructive destructive interference pattern of your acoustic beam within your medium. And what this alone can do is you can have it be you can use this type of a system to vary the frequency involved, or you can use it to manipulate the angle at which the acoustic beam is traversing in the medium, relative to the medium itself, right? So as you can kind of see here, and then this alone will allow you to perform the scanning maneuver, which I don't know, that's kind of an interesting technique. Seems somewhat inefficient to me relative to something like what we have down here. However, definitely has use cases. But down here you can have a more traditional beam where as it traverses through the medium, the acoustic waves, the wavefronts spread out a little bit. Excuse me. And then based on the location of the incident light upon here, you can get different types of different amounts of scanning involved. Excuse me. Now the finite number of scan angles that can be achieved, by the way, is a discrete number. So that's, I think, personally, I think that's very interesting in and of itself. It makes sense because you can only have so many diffraction angles before you'll eventually you will break Bragg conditions, right? So either the phase difference will not match up anymore, in terms of your wave vector, or your frequency components are going to be too far separated, and you can no longer obtain this nice sort of Bragg grading style reflection that we wish to achieve here. So within that kind of those confines, you do have this discrete number of allowable spots. And note that, nice thing with acousto-optics, something that I think is very interesting, is that whatever type of beam that you have incident, right, be it, a Gaussian beam or a Hermitian beam, whatever you're dealing with, same type of beam will be at the output. You can manipulate the beam, of course, as we've done here, where you can manipulate, the angle, excuse me, of it. In some cases, you can manipulate the frequency of it, and you can manipulate, a few other parameters. But the beam will take the same type, and as well as maintain its polarization. You can also use these techniques in switching applications and acousto-optic switching applications. Excuse me. So one simplistic kind of way of doing this here is, you have a monochromatic acoustic wave coming in. It's creating, your acoustic Bragg grading, let's say. You have your incident light, it gets diffracted, and it, forms one spot. And then you can vary this frequency to manipulate it and have it kind of traverse across multiple different spots here, as shown here. There are other, additional kind of fancier things we can do. So such as what we have down here, as you can see. This is what's called a spatial light modulator. So you can actually have it modulate n different beams by separating out the frequencies and the amplitudes of your acoustic waves in medium differently. So then in certain types of media where you can maybe have some sort of heterostructure involved here, like a piezo heterostructure wherein you perform your epitaxial growth. My guess is Professor Derrickson has discussed epitaxial growth slightly with you guys. If not, then the brief gist of it is that you can grow crystalline structures on top of other crystalline structures, a single atom at a time, such that you can get lattice matching in terms of lattice spacings as well as lattice type and orientation. You can perform things like strain engineering on top of that, but in effect, you're growing crystals on top of other crystals, atom by atom, to achieve a near perfect crystal at the end of it. So you can do this in what we call a heterostructure format, wherein you can sandwich multiple different specific types of materials involved here. And so in doing so, you can have the acoustic modes, the material handles be of different frequencies or different amplitudes here. And you can have multiple then, or one large, let's say, multichromatic beam of light coming in. And from there, you can split it off into multiple monochromatic beams. And then you can vary your amplitude and your frequencies here and get all these spots to up downshift as you would like. So this of course this kind of effect of switching allows for fairly high tunability. You can use it in applications wherein maybe you need to some communication system, let's say, where you have fiber input to your acousto-optic media, your switch, your spatial light modulator, and it's, let's say, multi-mode or multi-chromatic fiber. As the signal running through the fiber, at least it interacts with this acousto-optic material, and you can have it inject specific beams into specific regions of at the output, maybe coupling it to other fiber cables where it can then be sent off downline to wherever it's going, right? So that's just kind of one quick application that pops in my head for that. Of course, there are many others. Um, yeah. So one final effect, this is one that I think is probably the most interesting. This is kind of what got me into setting myself up on acousto-optic effects. Just because, I heard of this effect from a friend of mine about a year ago now, and I got really interested in it. I think it's very interesting how this piece of material can do so much, right, under the right circumstances. And so you can actually use acousto-optic devices, not only to perform the beam splitting and spatial light modulation and switching and everything, you can use it as a spectrum analyzer. I think that's really interesting. So again, by injecting multichromatic light incident to your acousto-optic medium, let's say you have multichromatic acoustic wave, being injected, then as long as all your Bragg conditions meet between each of the frequencies involved, both between your acoustic interaction and your incident optical interaction, then you can even get a scenario where this incident optical multichromatic beam will then split off entirely um, into a bunch of different monochromatic beams, monochromatic, of course, being each or one of the frequencies involved in the multichromatic incident beam. So kind of if it helps you visualize it, you can put like a white light input, and you can have multiple frequencies of your acoustic wave injected into your material, and then you will have multiple distinct individual color beams, optical beams at the output. So I think, again, yeah, this is really interesting. This can be further tuned and further modulated if you so choose to, which I think is kind of an interesting note. Um, Excuse me 1 second. Great. Yeah, so you can do this. This is a fairly interesting effect in my mind. You can use this in a bunch of different types of systems. You can create optical spectrum analyzers from this alone. Hint, hint, something will be important about this in a moment. You can use it as, like, let's say you have a heterodyne style structure where you need some sort of reference frequency sweep. You can use this type of system for it. If you need to create a Dirac comb, meaning you just have a bunch of different, excuse me, a bunch of delta functions at different frequencies, you can use a system like this to create such a thing, again, for a heterodyne or super heterodyne system, or, whatever other system you can think of. So I just think that this is kind of really neat effect. You can do this with very simple crystals. You can do this with, silicon dioxide if you so chose to, albeit you will probably have to dope the material slightly, but something as simple as that, you have it in the right shape. Yeah, you can create something like this fairly simply. So it's very interesting. And so that's sort of the last thing I wanted to talk about today in this lecture. I hope you guys enjoyed it. I hope you got something out of it. It wasn't super heavy on the mathematics. I tried to make it a little bit more qualitative. If you want to delve much deeper into the mathematics, the textbook covers a few additional concepts in a more advanced manner. Um, but the acousto-optic realm is fairly small compared to a lot of other major topics in, optics and photonics. And it's also one where we kind of, the consensus is that pretty much everything about it is figured out. Um, it's not a hugely complicated effect. I hope none of this was super confusing for any of you. Um, if yeah, if it was, I will be sure to kind of give my email either in the description of the video, or I will tack it on to the last slide here real quick. And so the nice thing with that, if you guys are confused anything, please feel free to reach out to me. I'd be happy to take any questions. Of course, I'm sure Professor Derrickson, when he gets back, would be happy to take questions from you guys as well regarding this topic. But I do hope that you found it fairly interesting. So moving on, lastly, to your guys' homework assignments. I hope that it's not too much. I tried to create it in, quote unquote, a Professor Derrickson style homework assignment. So there will be three parts. This is going to be the first part of the homework. So, you know, as I mentioned, I hope you guys were really paying attention to the spectrum analyzing or spectrum analysis functionality of Acousto-Optics, because you will be designing a spectrum analyzer using an Acousto-Optic cell. You can choose whatever Acousto-Optic medium you so choose. You can, whatever you want. You can have it operate in whatever frequency ranges you so choose. You can choose a different whatever topology you want. You want it to be a super, heterodyne, super heterodyne structure, go for it. If you want to do something as simple as kind of the example system that I have down here, that would also be fine. So, from this lecture, from the text, and probably from your own research as well, you will most likely need to do some of your own independent research, determine the specific laws involved in obtaining exact dimensions. Also, after you have all your laws kind of spread out here, determine the exact dimensions that you're going to need throughout the system. So, give me at least some information with regards to the fiber line that you have going on here. You don't need to go too in-depth on the fiber line. Go as in-depth as you possibly can on the Acousto-Optic cell. And then kind of give me, a brief description of the CCD array that you will be using. If you so choose to go with this structure, feel free to do something more complicated. If you can find something a little, more simplistic than this, yet still works and is still technically accurate, go for it. Please do provide some sort of image like this. If you do end up choosing a more advanced topology, let's say, then feel free to do it in more of a block diagram style. However, if you're going to do this, then please replicate this style of image. However, with exact dimensions involved, or just more detail, basically. Of course, do make sure to give an analysis of the acoustic wave or acoustic beam that you so choose to use, as well as the multi-chromatic frequencies that are involved here. So you have a good both qualitative and quantitative description of how you would utilize an Acousto-Optic cell in a spectrum analyzer. So this is your first problem. Moving on to your second problem, I would like for you guys to now design a Q-switching laser, again using an Acousto-Optic cell. Acting as an optical, you can actually have it be an optical switch, or you can have it be an optical modulator, your choice. But do describe that continuously. All material selection, operating frequencies, mode, whether it be a continuous wave or a pulse wave laser, the power of the laser, all custom, up to you. If you guys want to do if you want to design some sort of high power laser that takes, that utilizes Acousto-Optics, I wouldn't recommend it, considering that Acousto-Optics break down a little bit when you get to the higher power regime. But if you want to attempt it, go for it. With this one, I would like your analysis to be more qualitative than on the previous problem, slightly less quantitative, where I only want the quantitative analysis on the Acousto-Optic switch used. For this, you will unfortunately have to do some more external research. Please cite all your sources naturally, as you should in any and all case. So yeah, this will be, I think, a fun problem for you guys. Performing a nice qualitative description of an entire laser system. Hopefully you guys have covered lasers prior to this lecture. You should have, at least to some extent. And if not, the chapter on lasers and laser amplification, the chapters in the text are fairly readable. They're fairly easy to reach. And so happy reading on that one, I suppose. Finally, your third and final, your last question. I would like you to list 3 potential applications for an Acousto-Optic based scanning system. So, determine the application you get yourselves. Choose one of these types of systems, one of these applications from your list, provide full qualitative analysis. And there will not be too much need to go into the quantitative for this problem. I'm curious to see what you guys think are interesting applications for Acousto-Optics. Again, yeah, but you will need to provide a brief quantitative analysis on maximal scanning angle, as well as number of resolvable spots. So, you guys should know how to do this. It's fairly simple equations that I have described earlier in the lecture. Describe the acoustic frequency ranges needed to obtain this sort of operation within your chosen material. And again, cite all your resources. And just because, if I'm telling you guys to do it, I should do it as well. Here are all my references. And yeah, I will provide my email address, my Cal Poly email address in the description of this video. So if you guys have any questions, please feel free to reach out. I'd be more than happy to take your questions. And I'm sure as well, I'm going to say it again, I'm sure Professor Derrickson would be happy to take your questions as well. I hope you guys found this lecture enjoyable. I hope you all have a great rest of your quarter, and great rest of your week. And yeah, I hope to see you around on campus. If not, then bye-bye.